It sits in your pocket. It rests on your desk. It powers your journey home. An invisible force. A silent engine. We touch it, use it, and depend on it every second. Yet, we never truly see it. This is the story of the technology that powers our world. This is the blueprint of the lithium-ion battery. The world before was different. It was a world tethered by wires. Or weighed down by lead. Early portable electronics were feeble. They were constrained by their power source. Nickel-cadmium batteries had a frustrating memory effect. Lead-acid batteries were impossibly heavy. Technology was accelerating. But energy storage was a bottleneck. A wall. Progress needed a new kind of fire. A controllable, lightweight, chemical fire. The first spark came from an unexpected place. Exxon. The oil giant. The 1970s oil crisis was a shockwave. Exxon invested in alternative energy research. They hired a brilliant British chemist. M. Stanley Whittingham. Whittingham was fascinated by a unique concept. Intercalation. It was a gentle process. Not a violent chemical reaction. Imagine a bookshelf. Intercalation is like sliding books in and out. Whittingham wanted to do this with ions. He built a battery. One electrode was pure metallic lithium. The most reactive metal on Earth. A source of incredible potential. The other electrode was titanium disulfide. A material with a layered, molecular structure. A perfect bookshelf for lithium ions. When the battery discharged, lithium ions flowed. They slipped between the layers of titanium disulfide. When it charged, they flowed back. It worked. It was rechargeable. It had incredible energy density. But it was also dangerous. Metallic lithium is volatile. It could grow sharp whiskers called dendrites. These dendrites could pierce the battery's core, causing a short circuit, causing a fire. Whittingham's battery was a breakthrough. But it was too wild to be tamed. Exxon eventually abandoned the project. The idea, however, was out. A new mind took up the challenge. Across the Atlantic, at Oxford University. Professor John Goodenough. A physicist who had turned to chemistry. He saw the genius in Whittingham's work. But he also saw its fatal flaw. Goodenough theorized the problem was the cathode. The titanium disulfide bookshelf. He believed a metal oxide would be far superior. It would hold more ions. And it would produce a much higher voltage. His team began a systematic search. They tested different materials. In 1980, they found it. Cobalt oxide. When paired with a lithium anode, the result was astonishing. The battery's voltage instantly doubled. From 2 volts to 4 volts. This was a monumental leap. It quadrupled the potential energy storage. Goodenough had created the fundamental architecture. The core blueprint for nearly every modern lithium-ion battery. But the original danger remained. The anode was still pure, volatile metallic lithium. The problem of the fire was still unsolved. The final piece of the puzzle came from Japan. From a corporate lab. Asahi Kasei. An engineer named Akira Yoshino was tasked with creating a safer battery. He knew of Goodenough's powerful cathode. But he refused to use the dangerous lithium metal anode. He needed a new material for the other side of the battery. A material that could safely store lithium ions. Just like the cathode did. He began testing various carbon-based materials. He landed on petroleum coke. A byproduct of oil refining. It had the right structure. It could absorb and release lithium ions safely. Without the dangerous dendrites. Yoshino built a new prototype. On one side, Goodenough's cobalt oxide cathode. On the other, his own petroleum coke anode. There was no metallic lithium inside. Only its ions, shuttling back and forth. It was stable. It was safe. It held a powerful charge. In 1985, the puzzle was complete. Whittingham's concept. Goodenough's cathode. Yoshino's anode. 3 minds, across 3 decades, had created the blueprint. A Nobel Prize-winning design. But it was still just a prototype in a lab. To change the world, it had to be manufactured. By the millions. The late 1980s. Japan was a nexus of consumer electronics. Companies were locked in a battle for miniaturization. Sony was a dominant force. Their Walkman had changed how we listened to music. Their Handycam put a video studio in your hand. But their ambitions were limited by battery life. Sony's engineers saw the lab reports. They understood the potential of Yoshino's prototype. A small, lightweight battery with 4 volts of power. It was the key. The key to smaller devices. The key to longer runtimes. Sony made a historic decision. They would be the first to commercialize this technology. It was a colossal gamble. The chemistry was still new. Manufacturing it at scale was an unknown frontier. An army of engineers was assigned the task. The pressure was immense. Failure could mean financial ruin and public disaster. They had to turn a lab experiment into a safe, reliable product. First, they needed a standard shape. A unformed factor. They designed a small cylinder. 18 mm in diameter. 65 mm long. They called it the 18650. This single cell would become a global standard. Inside, the engineering was intricate. The cathode and anode were not solid blocks. They were thin foils, coated with chemical slurries. Separated by a micro-perforated polymer sheet. This separator was critical. It allowed ions to pass through. But it prevented the electrodes from touching. Preventing a catastrophic short circuit. The foils were wound together tightly. A chemical jelly roll. This roll was inserted into the steel can. Then, a liquid electrolyte was injected. The lifeblood of the battery. The medium through which the ions would travel. The can was sealed. But the engineering didn't stop there. Sony's team was obsessed with safety. They built in multiple layers of protection. A pressure-activated vent to release gas if the cell overheated. A small circuit that would trip like a fuse if the temperature rose too high. A positive temperature coefficient device. They created the first battery management circuits. Tiny electronic brains. They prevented overcharging. They prevented overdischarging. This wasn't just chemistry. This was mechanical engineering. Materials science. And electrical engineering, all in one tiny package. In 1991, Sony launched its first product. The CCD-TR1 Handycam. Powered by the first commercial lithium-ion battery. It was a revolution. Suddenly, devices were untethered. They ran for hours, not minutes. The world took notice. The gamble had paid off. Soon, a firestorm of competition erupted. Panasonic, Sanyo, Toshiba. South Korea's LG Chem and Samsung SDI joined the fight. The battleground was the factory floor. Who could build the cleanest rooms? Who could perfect the slurry coating? Who could increase manufacturing yield by a fraction of a percent? Patent wars were waged in courtrooms. Companies reverse engineered their rivals' cells. They fought over tiny improvements in electrolyte chemistry. Or separator polymer formulas. This brutal competition had a stunning effect. Prices plummeted. Performance soared. Energy density increased year after year. The cell that powered a camcorder in 1991 was ready to power the mobile phone revolution of the late 90s. And the laptop boom of the 2000s. The 18650 cell became the invisible brick. The fundamental building block of a new, portable world. For 2 decades, the mission was clear. Powering smaller and smaller devices. But a new, far larger challenge was emerging. The automobile. For a century, cars had run on gasoline. Electric vehicles were a niche idea. Hamstrung by the weight and weakness of lead-acid batteries. Lithium-ion changed the equation. A small startup in California saw the potential. Tesla Motors. Their idea was radical. They would not invent a new battery. They would use the humble 18650 cell. The same cell found in laptops. But they would use thousands of them. They assembled 6,831 cells into a single pack. This was an engineering challenge of immense scale. A single cell failure could not be allowed to cascade. Tesla's engineers designed a new blueprint. A battery pack as a complex system. Each cell was monitored. Its temperature and voltage were tracked in real time. This was the job of the Battery Management System, or BMS. The digital brain of the pack. They designed intricate cooling channels. Liquid glycol snaked around every cell. Wicking away heat. Keeping the entire pack at a uniform, optimal temperature. The Tesla Roadster proved it was possible. Lithium-ion could power a car. And the industry pivot began. The demand for batteries was about to explode. The scale was no longer millions of cells. It was billions. Then, trillions. This shift created a new world order. Japan and Korea had dominated the first era. But China saw the future. Through massive government investment and strategic focus. A new giant emerged. CATL. Contemporary Amperex technology. They built factories on a scale never seen before. Gigafactories. Sprawling complexes where robots work in perfect sync. Rivers of chemical slurry are coated onto foil kilometers long. Lasers cut and stack electrodes with microscopic precision. The old 18650 cell was still used. But new formats emerged, tailored for vehicles. Prismatic cells. Hard, rectangular cans, easy to stack. Pouch cells. Flexible, foil-like packages. They eliminated the steel can, saving weight and space. Each format was a different engineering trade-off between energy density, cost, lifespan, and safety. Inside these modern packs, the blueprint is more complex than ever. The chemistry is constantly evolving. New ratios of nickel, manganese, and cobalt. Or the rise of LFP, lithium iron phosphate. Cheaper, safer, and longer lasting, with less energy density. It's a constant dance of innovation. Driven by data from millions of vehicles on the road. Today, the lithium-ion battery is the foundation of our energy transition. It stores power from solar panels and wind turbines. It balances the electrical grid. It powers the tools and trucks that build our world. New frontiers are on the horizon. Solid-state batteries promise a leap in safety and density. Sodium-ion offers a future without reliance on scarce lithium. The challenges of mining and recycling loom large. The blueprint must continue to evolve. But look again at the device in your hand. The car in your driveway. Inside is not just a component. It is a legacy of science. A story of risk and competition. A masterpiece of engineering. It is the quiet, invisible engine that gave us the modern world. And holds the blueprint for its future.